Hey class, hopefully your exams went well. For those of you who put in the work, I'm very, very proud of you. It's not an easy exam, but I know y'all prepared and you crushed it. So let's go ahead and get started. Welcome to Reading Recap 5. Aha. Okay, so our reading for today is going to start off on page 377. So if I turn to 377, we see the section called DNA polymerase 3 is a replicated polymerase in E. coli. That is over her. So what I want you to know is that essentially we're starting off switching from a eukaryotic system to a prokaryotic system. We spent last lecture before the exam talking about polymerase 1, and this time we're talking about polymerase 3, and it works as a great example for how DNA replication occurs because in prokaryotes it is a lot simpler. So on the next page, they talk about the POL3 holoenzyme. So know on this figure here, 11.4, kind of how you have this assembly of these three different polymerase 3s plus these beta clamps. We'll talk about beta clamps in class today. And the core to allow us to do DNA replication across the fork, doing both the leading strand and lagging strand at the same time. As we continue to read, so we said page 377 to 379, that's basically what you need to take away from there. We're going to skip to 368. So going a little bit backwards. 368. Oh, I can't. Skipping forward. 381. Oh my gosh. Wow, Queen. Okay, so skipping forward to 381. So in the next couple of pages, starting from many different proteins advance a replication fork, that is right here. I want you to basically focus on these key proteins that are involved in DNA replication. So we go through helicase. Number one, we're going to know that. You'll see it in your reading quiz. After helicase, we're basically going to hit on a topoisomerase. And I literally have these labeled in my textbook. So for example, topoisomerase, that's the number 2 thing. And then I have primase, that's the number, where's the mirror? Okay, number 3 thing, primase. So follow through and know each of these things. If you look at figure 11.9, it shows different activities that are required out of replication fork. This sequence of events is really important, and it'll be an easy way for you to review and just have that background-based knowledge of what order do we go into in order to start DNA replication. An experiment that we're going to use for application in our lecture is going to be this figure. It's 11.20, and basically it's an experiment that shows us how we're able to determine the direction of a helicase. So this is going to be something that you want to refer back to after we have class. Okay, so we keep on going. We hit single-stranded binding. Single-stranded DNA binding protein. Once again, all these different things we're going to go across in class, but just know that there are definitions here in the textbook for you. And so replosome is another thing that I do want you to know what it is, and basically interaction of the helicase and primase coming together. That's going to be important. And then what's really difficult, at least for me, is kind of conceptually wrapping my head around how we're going to move or replicate the leading strand and the lagging strand at the same time. And there's this whole thing called the trombone model. I'm actually going to post a video of it on our, I don't like how it looks. On the Canvas page. So a video of how trombone model actively works. So you can see the whole like holoenzyme replicating a fork and how having these 3 different polymerase 3 cores allows us to amplify 2 strands that are anti-parallel at the same time. There's a good depiction of it in figure 11.22. And so if your mind isn't comprehending how this actually works, figure 11.22 is a good resource, and also the video that I'm going to post on Canvas is a great resource. Okay, so it brings us to the end of the first set of reading. That's where we are. We're 381, 387. Page 386 to 387, there's not too much you need to focus on from the textbook, but basically knowing what the Okazaki fragments are. So now I'm going to skip backwards to page 221. 221. 221. Okay. 221. So the first set of readings basically talking about DNA replication in vivo inside of a cell. And when we jump backwards to 221, we're doing DNA replication in vitro outside of the cell and the things that are necessary. So what I want you to do is kind of keep in vivo versus in vitro separate and think of the things that you need. And the main thing that we're going to talk about for DNA application in vitro is PCR, or polymerase chain reaction. So polymerase chain reaction is going to need 3 different things. On page 222 is where majority of information you need is for how PCR works. We are going to go over PCR extensively, and then we're going to talk about exactly how we design primers for PCR. The figure that is on the following page, on page 223, which is 7.9, figure 7.9 will help you understand how we actually amplify only a piece of target DNA as opposed to all the DNA that's in the sample. We will walk through this in class, but I promise you that this figure will be really helpful in your understanding of how primers work in order to amplify whatever genetic information is in between those two opposing primers. There's a little bit of distinction between different types of PCR. I marked it in my book because I think it's important, but I'm not going to test you on it. But reverse transcriptase PCR versus quantitative PCR, they are a little bit different because of additional steps that are there. But really what I want you to take home is the information on page 222 that describes PCR, what is needed for PCR to occur, including the fact that instead of ATP, you have heat, that you need in the reaction, your DNA sample, that you need your pair of primers, and then also the reasons why the primers will bind to the DNA as opposed to DNA binding to DNA. 222, that whole left side of the page is super, super important. Okay, so we said all the 223, that's to the figure. Like I said, figure is great. We're going to skip over to page 251. 251 basically is the backstory to how we got a polymerase that works for doing in vitro synthesis of DNA. Originally, the person who actually created DNA, Kary Mullis, he used a polymerase that essentially, after every time we did a step where we heated up the sample to denature the two pieces of DNA, the polymerase would actually denature also, and you had to add in polymerase every single time. But someone else who was basically studying a polymerase in an environment from a bacteria that lived at very, very high temperatures was able to get what we call a thermostable DNA polymerase called Taq polymerase. So this is what is conventionally used during our DNA synthesis or PCR that we do in vitro in laboratories. So by putting together the whole concept and idea of PCR with a heat stable Taq polymerase, we have this beautiful thing that we can do where we amplify DNA very, very easily in a laboratory. And it's one of those techniques that anyone who does biological sciences just knows how to do. Okay, and so that's basically how we were able to do PCR, and know that the Taq polymerase and the fact that it's heat stable is very important. Now, our last bit of reading for today is going to 399 to 403. 399. So I think twice I have told you that we are going to come back to telomeres and telomerase and end replication problem. 399 to 403 basically talks about the end replication problem and what it is and how telomeres solve it. So I think this reading passage is actually really, really nice. On page 400, it talks about how telomerase was discovered. We talked about it a little bit during one of the breaks in class. It was a cool story. It's a really, really cool story to read. But the things that we really want to understand from page 400 is basically that telomerase includes the reverse transcriptase and the non-coding telomerase RNA. So you need the reverse transcriptase, and then you also need that primer that it uses in order to extend the 3' end. So what I want you to note, based off of 399 all the way to 403, is essentially how telomerase works. So after you finish reading, take some time, sit down, look at page 402, where you're on figure 1136. Figure 1136 shows and diagrams how you actually extend the end of that 3' overhang of DNA. And at the end of the day, you extend it, you fill it in with DNA from the other side, because now we're able to do that, but then you still have an overhang. And know that that overhang is going to be protected by telomerase. There's a protein that protects telomerase, telomere DNA binding proteins. Very straightforward. So just know that the ends of the telomeres are protected. So once again, page 402, this figure will be your best friend for going back and making sure you understand how telomerase works. You do need to know this. So lastly, you have a highlight on page 403 talking about the relationship between aging and telomeres. Basically, with aging, our telomeres get shorter, and I think is very well related. Experiments have been really interesting because if you take a mouse and you knock out telomerase, the mouse lives just as long. And what we see is that the stability of the DNA seems a lot more important for cancer and stem cells as opposed to longevity of the organism overall. But that's it for our reading, and I'm excited to see y'all in class. All right, bye.